Hello everyone, this is Professor Lee. Let's solve this problem. In this problem, we're going to practice this topic equilibrium in 3D. We have one sign and then its weight is given 500 newtons and then our body is supported by a ball and socket joint at point A. And also two cables were used as a support types. From this, what we have to do, we have to express the reaction force from the cable. Thankfully, cable from B to C is provided, but we still have to find the cable reaction. That's what we have to express as Cartesian as well as our weight. From this, what we're going to do, we're going to apply equilibrium equations and we're going to express those equilibrium equations for the forces and moment about each axis. So it's good practice to take care of the 3D problems, how to express our forces as Cartesian vectors, which was topic 4, and then we're going to apply those vector analysis and scalar analysis to identify equilibrium in 3D problem. Let's take care of the given information. The support type at A is given ball and socket. We do know the characteristic ball and socket. Ball and socket will not allow the translations in any directions, but will allow rotation in every direction. Therefore, three unknowns in translation in X, Y, Z directions will be there from the ball and socket. Cables, always we're going to start from tension. This is our assumption, then we will see. Okay, then weight is given as 500 newtons, and then point information was given, and then these points are important because we have to find the tension information from the body with these two cables. So point B is on the y-axis, therefore other x and z coordinate will be 0. Then point C is on the x and z plane, therefore y coordinate is 0. For the point D, it's still on the x and z plane. Therefore, y coordinate is 0. Let's take care of the unit for the point. Following the coordinate system in this problem, it's meters for the point. Point is not a vector. Point is a scalar quantity. So from this, we have to find the tension from the cable specifically at B to D, and also we have to provide the weight of the sign as Cartesian vectors. Tension T of BD, this is a vector, and then also the weight of the sign as Cartesian. And then once we have these vector expression of these forces, then we're going to apply scalar analysis method to apply equilibrium equations for the forces and the moment. That's what we're going to do. Let's start our solutions. Very first step, let's define our coordinates. So these directions are going to be our positive directions for each axis. Counterclockwise for the moment will be our positive direction in this solution. Let's start to express our tension from the cable B to D. Cable tension, we do have a point information. Therefore, to express our this tension in 3D, our strategy will be position vector information because points are given from the point B and D. So once we have these 2 points, we can apply head minus tail to find the position vector. After that, express our unit vector from the position vector. First of all, we're going to identify what is the position vector. Tension from B to D. Who is the head? Point D is the head and the point B is a tail. To find the position vector, we need this formula, head minus tail. So let's write down head, arrow direction, which was point D. Then who is the tail, which is the starting point of a vector, therefore point B. So we have to apply the formula head minus tail to find the position vector. Scalar algebra for each component, minus 2 minus 0, therefore minus 2i. 0 minus 2 or minus 2j vector. 1 minus 0 plus 1k vector, and the unit should be meters. Position vector has the unit, but we are going to convert this one into the unit vector. Can be expressed as position vector R of BD, but position vector has its own unit. How we can make them equal? Divided by its own magnitude of the position vector. Numerator, we just copy this one, and denominator is going to be each component squared. Therefore, minus 2 squared plus minus 2 squared plus 1 squared. Numerator also has a unit from the position vector. Magnitude also carries a unit. Meters cancelled out. The unit vector only has the magnitude as 1. Let's write down our answer here. T of BD tension can be expressed as, we don't know the magnitude of T of BD tension yet, but applying equilibrium equations, we can find the reaction of this tension. But we do know the direction from the unit vector we just found, U of BD. So it's going to be minus 2 over 3 T of BD I vector, minus again 2 over 3 T of BD J component. K component will be 1 over 3 plus T of BD K vector. The unit should be Newton. Then weight was only in Z direction because gravity directions in this system, it's going to be Z direction. Other components, it's going to be 0. We do have magnitude for the Z and then downward direction. Therefore, minus 500 K component unit must be newtons. So we expressed our force as Cartesian successfully. Then we have to move to the scalar analysis to apply equilibrium equations. For the equilibrium equation problem, we need free body diagrams. So let's construct our free body diagram for this problem. Start from FBD under bar. So what we're going to do, we're going to place our body on this coordinate system. X, Y, Z coordinates are there, and then still using the blue color, draw and outline the body. So, okay, then let's take care of the important geometric information. Point 8, origin in our coordinate system, and very end here, point B. Let's indicate on our outlined body. These are important because reactions are applied there. And also, we're going to indicate point G because at the G, our weight will act. Outline the body is done. Then now we have to show all the forces acting on it, including active and reactive force. We have an unactive force, which is the weight of the sign. So here, downward direction, we do have weight 500 Newton in terms of the magnitude. Then now green color, reaction forces. We're going to start from point A, then let's move to point B. At A, ball and socket cannot resist the rotations in any directions, but will resist the translations in any directions. And therefore, we're going to have 1, 2, and 3 in terms of translation reactions from the ball and socket. In terms of the arrows, we don't know yet, so let's temporarily set these directions are going to be reaction forces, and then we're going to apply equilibrium equations to see the real confirmed reactions to make our body in equilibrium. Then let's move to point B. Point B, we do have two tension here, B to C and B to D. So let's clearly indicate those point information so that we can clearly indicate the line of action of these tensions. Point C is onto XZ plane. D also was onto XZ plane. So this is point C, point D. According to that one, we can actually sketch the line of action of those tension from these two cables. Tension from the B to C, and let's label this is T of BC, and then tension from the B to D, and then let's label this will be tension B of D. We're almost done, so let's provide the important geometric information. A to G is 1 meters. G to B is also 1 meter. More, no less. That's our free body diagram. So far, we represented our forces as Cartesian using vector analysis. T of BC was given from the problem. We found T of BD using the position vector strategy, and we also expressed our weight of the sign as Cartesian vectors. So all forces were expressed as Cartesian vectors, so we finished our vector analysis. That means using this free body diagram, we are ready to apply equilibrium equations to find these reaction forces. In this problem, we have to provide 3 equilibrium equations regarding forces. Also, we have to provide 3 equilibrium equations for moments about each axis. For this, we're going to use scalar analysis. We can start from Fx equal to be 0. Summation of all the forces in x directions must be balanced. We're going to start from point A, then let's move to G to B. That's going to be our order of work. Starting from A of x, yes, we have to account for this A of x, and we temporarily set this is a positive direction. So A of x. A of y, no, this is about y component. A of z, no, this is about z component. Let's move to the point G. Point G, we have one weight in z direction, therefore this is not about x. Let's move to point B. Point B, we have 2 tensions, which is T of BC, T of BD. What we're going to do, we're going to coming back our result here in terms of vector analysis. Then we're going to see whether we have x component of this one. Yes, we have an x component here and also x component here for the T of BC and BD respectively. So we have to account for them. 1 over 3 T of BC, let's take care of, and let's move to T of BD minus 2 over 3 T of BD must be taken care of, but here weight, we do have 0 for the x component, therefore no contribution to the x. They must be balanced. Similarly, we're going to move to summation of all the forces in y directions must be 0. Let's start from point A. A of x, no, but A of y, yes, and we set temporarily that one as positive, therefore plus A of y. Then we're going to move to point G. Point G, weight, again, the y component is 0 in this our vector analysis, so therefore we have to pass this point to G. Then let's go to point B. Point B, 2 tensions, T of BC, T of BD. Yes, we do have a y component for the T of BC minus 2 over 3 T of BC. Then let's move to T of BD. Yes, again, we do have minus 2 over 3 T of BD. They must be balanced again. Then lastly, we have to apply summation of all the forces in z direction also must be balanced. Again, we're going to start from point A. A of x, no. A of y, no. But A of z, yes, positive. That's what we set in the free body diagram temporarily. Then let's move to point G. Yes, W has z component minus 500. Then point B. Point B, 2 tensions are there. Tension T of BC, yes, z component is plus 2 over 3 T of BC. Then let's move to tension of B of D. Yes, we have z component, which is 1 over 3 T of BD must be balanced. So all the 3 equilibrium equations for the forces, we finished. Then now we have to move to the moment about each axis. It's good time to review how to calculate moment about axis in 3D using scalar analysis. So in scalar analysis, we're going to find the magnitude using this formula. Moment will be found by moment arm times absolute value of the force. In 3D, what was the moment arm? Moment arm is a perpendicular distance to the axis we're considering, but also simultaneously perpendicular to the line of action of the force. What that means is that if the force vector we're considering is parallel to the axis we're considering, then there will be no moment, because that way we cannot have a perpendicular distance to the axis. But also, if that force is passing through the axis, then we will also have no moment arm because we will not have the perpendicular distance to the axis. Checking this one, we are ready to consider the moment about each axis. So let's construct the equilibrium equations. Moment about x-axis. All the moments about x-axis, they must be balanced. We're going to start from this point A, then let's move to point G and B. In this free body diagram, at point A, all these 3 forces are passing through the x-axis, and therefore A of x, A of y, A of z cannot create moment about x-axis. Then let's move to point G. 500 newtons will create moment about x-axis. Yes, because this line of action of W is not passing through the x-axis, but also it is not parallel to x-axis. Therefore, it will create moment about x-axis. Therefore, who is the moment arm? Moment arm must be perpendicular to the axis we are considering, therefore x, and also perpendicular to the line of action of the force. Who is it? Z. Therefore, we have to read y coordinate in terms of the moment arm for this W about x-axis. This 1 meters will be the moment arm. Then let's call, how we can call, minus. 1 meters was the moment arm, and then absolute value of the force, and then applying right hand rule, minus was the direction of the force. Then let's move to point B. Point B has two tensions, T of BC and T of BD. We're going to start from T of BC. T of BC, let's graphically resolve this one into this free body diagram here. So T of BC can be resolved into x direction and the y opposite minus and z vertical positive. Then let's consider each component, whether these components can create moment about x-axis. For the x component, no, because it is parallel to x-axis. What about y component? It's literally passing through the x-axis, therefore no moment arm from it. But what about z component? Yes, z component will create the moment about x-axis because it's not passing through the x-axis. Also, it's not parallel to x-axis. Therefore, T of BC z component will create moment about x-axis. So moment arm must be perpendicular to the axis we're considering, but also perpendicular to the line of action, who is the z. So therefore, still we have to read y coordinate in terms of the moment arm. 1 plus 1 perpendicular distance from the axis to the line of action of the force. That's the moment arm definition. 2 meters must be the moment arm for the z component of T of BC. Moment arm is 2 meters, and then for absolute value of the z component, 2 over 3 T of BC. Then how we can call this one? Thumbs up posture. We can call this one, therefore, pause. Similarly, let's graphically express T of BD in this free body diagram. T of BD, x component is minus, therefore in this direction. T of BD, let's use this color. And then y component is still minus, therefore opposite direction. Z is positive, therefore upward. So very similar scenario compared to the T of BC for the T of BD. Then let's take care of each component, whether they can create moment about x-axis. First of all, x-axis, for the x component, they are parallel. Therefore, they cannot create moment about x-axis. Y-axis still cannot create moment about x-axis because it is passing through. But z component will create moment about x-axis similarly as like T of BC z component. Then who is the moment arm? 1 plus 1, 2 meters will be the moment arm because perpendicular to the x-axis and the line of action of T of BD, z component, there was z. Therefore, we have to read y coordinate, which is 1 plus 1 meters, 2 meters will be the moment arm. How we can call thumbs up posture. So very similar. So moment arm is 2 meters. Then absolute value of the force, therefore 1 over 3 T of BD. Then applying right hand rule, we checked it must be positive directions. They must be balanced. Let's keep working. Summation of all the moments about y-axis also must be balanced. Starting from A, AX, AY, AZ. All these three forces are passing through the y-axis. So therefore, they cannot create the moment about y-axis. Let's move to point G. Point G is passing through the y-axis. Therefore, this W will not create the moment about y-axis. What about point B? Point B, we do have a T of BC, T of BD. All the force components, X and Y, Z components of these two tensions are on the y-axis, Therefore, they're passing through the y-axis. Therefore, they cannot create moment about y-axis. Considering the characteristic of the system design, these all the forces cannot create moment about y-axis. Therefore, no moment about y-axis. Lastly, summation of all the moments about z-axis also must be 0. Starting from A of x, A of y, A of z. All these three forces are passing through the z-axis. Therefore, they cannot create a moment about z-axis. Then let's move to point G. Line of action of this W is parallel to z. Therefore, it will not create a moment about z-axis. Then let's move to point B. Point B, we have two tensions. Let's start from T of BC, starting from X component, darker of the green color. That's X component. X component can create moment about Z-axis. Yes, because it is not passing through the Z-axis. Also, the line of action of this X component is not parallel to Z. So moment arm must be perpendicular to the axis we are considering, therefore Z. Simultaneously, also perpendicular to the line of action of the force, therefore X. We have to read y coordinate again. So therefore 1 plus 1, starting from Z to the line of action perpendicular distance. That was the moment arm definition. Therefore starting from here, 1 more 1, therefore 2 meters will be the moment arm. How we can call this one? Thumbs down posture, we can call this X component of T of BC. Therefore, minus 2. Then, absolute value of the force of the T of BC X component, 1 over 3 T of BC minus posture worked well to call that force. Let's move to Y component. Y component can create moment about Z. No, it is passing through the Z-axis. Therefore, no creation about Z-axis. What about Z component? No, because it's parallel to Z-axis. Therefore, no creation from the Z component. Then let's move to T of BD starting from X component. Let's look at this lighter of the green color for the T of BD X component. T of BD X component will create moment about Z-axis. This is not passing through the Z, also not parallel to Z. Then who is the moment arm? Perpendicular to the Z and then X component, line of action. Therefore, who must, in terms of the moment arm? Y coordinate. Again, 1 plus 1 must be the moment arm. So we can call this one as positive. So we see the moment arm for this one should be 2 again. Then this X component was create moment about Z-axis. Take absolute value of the force. Therefore, 2 over 3 T of BD from the X component of T of BD. Then we were able to call that direction with positive direction. Let's keep working for Y and Z components of the T of BD. Y component of T of BD is still passing through the Z, therefore no creation about moment about Z-axis. And then Z component is parallel to Z, no moment from the Z component, moment about Z-axis. These two components must be balanced. So we created 3 equilibrium equations for forces, 3 equilibrium equations for the moment about each axis. And we also successfully expressed our forces as Cartesian using vector analysis. This is about it. Thank you everyone. See you next time.